Last time we discussed about the fundamentals of fluid dynamics. This was the syllabus we have. We we discuss about the various scientists or researchers, various scientists who work for the fluid mechanics. We discuss this topic also. What is CFD? Why we require the CFD? What are the advantage? What is the process? What are the applications? The all the details we have discussed last time. This is the complete process, step by step process through which we can execute the simulation and we can get the results. We can analyze the results for better design of the particular system. These are the softwares, grid generation softwares. Then these are the post processing softwares, panel views, inside tech plot where we can visualize the colorful contours and we can analyze we can identify the property at particular point. The modeling is the mathematical physical problem formulations in terms of continuous initial boundary values problem, which it may be in the form of partial differential equation with the appropriate boundary conditions and relation conditions. Modeling is not only about the creating geometry, it includes geometry and domain coordinates, coordinate equations, flow conditions, initial and boundary conditions, selection of model for different applications. Okay, so there are three methods, three techniques: coordinate system, which is called Cartesian, cylindrical, and spherical. Then we have seen the Gurney equations, Navier-Stokes equation in three Cartesian coordinate system, where continuous equation in the left side we are having continuous equation. So local acceleration with which is reference to the time derivative. Then there is a convection which is phase derivative, and in the right side you can see piezometric pressure gradient, and in the last term which is a viscous term. So continuity equation, equation of state, and relay equation. This will be help us to identify or to develop the complete mass equations for the solution. There are various models that we are covering in the syllabus also. Initial boundary conditions, modeling, all the things we have discussed last time. Now today we will be seeing the essentials of fluid mechanics and heat transfer. So essentials, what are the basic thing, what the the CFD syllabus required is the fundamental of some laws, right? So fundamental principles which are necessary to understand and apply the knowledge of CFD. So these principles are rooted in physics and are expressed mathematically through equations. Okay, so these equations we are going to study today. So conservation of mass, which we also call as a continuity equation. The principle states that the mass of fluid entering and leaving a system remains constant, right? So if we talk about the differential form in 3D, so dou rho by dou t have the fundamental principles that governs fluid flow and heat transfer. So these principles are essential for building the equation solved in CFD simulation. So three primary conservation laws, that is mass, momentum, and energy, which are the core, and along with the transport mechanism like conduction, convection, and diffusion. The first law is the conservation of mass, also known as continuity equation. It ensures that the mass of the fluid remains constant in a system. So mathematically, this is expressed as a rho, which is the density of the fluid, and this equation dou rho by dou t plus nabla or del dot product of rho and velocity field. So this is the summation will be, this summation will should be equals to 0. Okay. So as I said, if the through the pipe, if the water is entering at the mass of 5 kg, same mass should exit at the outlet. So we are assuming there is no losses in terms of leakage or accumulation within the system. Second law is about conservation of loss is conservation of momentum, which is generally called as a Navier-Stokes equation. These equations describes how momentum is transferred within the plate due to force like pressure, viscosity, and external force, right? Like body gravity. So if we write the momentum equation in differential form, which we already saw in the previous slides. So rho dou V by dou T plus dot product of V by nabla into velocity again, it should be equals to minus of nabla or del P plus mu nabla square P plus S. So what is rho? Fluid density, P is pressure, mu is dynamic viscosity, and nabla square by V is viscosity term, and F we say it is external force. So if we take the example modeling airflow over aeroplane wing, so always we are predicting the analysis by applying the Newton equations which predicts the lift and drag force over the plate. Then conservation of energy. If we say energy conservation describes how thermal energy is conserved within the system, accounting for conduction, convection, and external heat source. Right. So whenever there is an involvement of temperature term, then always consider the thermal energy to be. So differential form, if we write, then dou rho E by dou T, there is a specific internal energy plus nebula product dot rho EV is equals to minus nebula plus Q, where Q is heat flux, which we know minus K delta T plus dissipation function plus Q, which is a heat source. So this is the differential form of conservation of energy. So predicting the temperature distribution in a car engine block under high thermal load, we can consider it as an example for this. Okay. So just remember, whenever there is an involvement of temperature, always the conservation of energy law comes into picture. Okay. Now transport mechanism, as I said, whenever there is an involvement of the principle physics, then we always talk about some laws. Now transport mechanism, where how the energy will be transferring from one section to another section. That section we are discussing, that generally we involve conduction, convection, and diffusion, because there is always involvement of transfer of energy. Heat transfer due to the molecular interaction, which we govern through the Fourier's law of heat conduction. Now Q is equals to minus K delta T, where K is thermal conductivity of that particular solid or fluid, and delta T is the temperature gradient. Because whenever there is a temperature gradient, then only there is a possibility of energy transfer, it transferred due to the molecular interaction. For example, take heat conduction through a metal rod. So CFD simulation will help us to predict the steady state temperature profile over the particular distance or particular thickness. So which will be help us to see how the heat is conducting from one end to another end. Right? And convection is, as we know, heat transfer through the fluid motion, where we can give the Newton's law of cooling. Q is equals to HA delta T, where H is convective transfer coefficient and A is the surface area and delta is the temperature difference. So example, if we take modeling air cooling in a computer CPU using a fan, as well in our laptop also we can see the cooling fan we are providing, which helps us to extract the heat or remove the heat which is generated inside the top. Okay. And diffusion. Now, in the convection also there are two types: forced convection and natural convection. If we are providing some external fan or blower over the heat source, then through the convection it can transfer the heat to the atmosphere. And if we natural convection is without addition of any external force to fan or blower, then if there is a heat transfer, then you say it is natural convection. Now diffusion, moment of species, heat or momentum due to gradient. Mass diffusion, we generally say it is a fixed law, which J equals to minus D nebula C or del C that D is a diffusion coefficient and C is a concentration. Okay. So whenever there is a transfer of mass, that time we say it is a diffusion. Now, it's like in the case of cooling tower, if you take the example of cooling tower, there is always the air is always air carries the mass or water particle along with it. Also, simulating the pollutant dispersion in the river is addition of mass in the particular river. So that is, we say it is a diffusion. So this comes under the transportation mechanism. Take the example again with the particular problem. So analyze the airflow through the rectangular duct where it is supplied to the wall, and air will carry the heat. Then that time, if we say the mass conservation, then mass enters will be equal to the mass outlet. So mass flow rate at the inlet is equals to mass flow rate at the outlet. So rho AV, rho is density, is area, cross section area, and V is a, so mass entered here at this section, we can say mass in will be equal to the rho A V equals to mass flow out. So what is A is a cross section area. Suppose A and B is the length and height, then A into B will be the cross section area, and V is the velocity enters. Momentum conservation, which we can analyze with the help of linear stroke equation to determine the velocity profile considering the viscous effect. Okay, so this is the equation rho dou V by dou T is equals to minus dou P by dou X plus mu dou square V by dou Y square. So in this case, we are saying the velocity along the particular X direction, right? Conservation in now next come to the conservation energy equation. So predicting the temperature distribution in the duct, we can utilize this particular energy conservation. So dou Cp bracket dou T by dou T plus V dou T by dou X equals to K dou square T by dou Y square, which is 1D equation for energy conservation. This is a 1D equation for momentum conservation. If you see the 2D, then we can see the specific at the wall and temperature distribution higher near the heated wall. If we see there, if this is a heated surface, suppose this is the heated surface, this surface is heated, outer surface is heated, then more heat at the wall and lower at the duct. So temperature profile we can see in this way. So more heat at this particular wall, and in the case of velocity, higher velocity at the center and less velocity at the border, at the boundary. So this is the simple concept we can understand with the help of particular problem. Now come to the differential form of conservation of mass. The conservation of mass ensures that the rate of change of mass is controlled due to equal and net mass flow across the bond. So let's start with the conservation of mass, which is also called as a continuity equation. This principle ensures that the mass of the fluid system is conserved over the time, as we know. So accounting for the inflow and outflow of the fluid in control. Now, if you see the equation in the conservation form or in the differential form, so dou rho by dou T plus del or nebula rho V should be equals to 0, where dou rho by dou T is the rate of change of density with respect to time, which is generally for the compressible fluid, and del product del rho V is a divergence of mass flux indicating the rate at which the flow out of the volume. If there is an incompressible flow where density is constant, this equation can be simplified simply as this term nebula dot rho V. That's it, will be equals to 0. So this is a differential form. So consider if we take the airflow to the duct, the continuity equation ensures that the mass entering the duct equal to the mass exiting the duct assuming no leakage or mass addition, right? So this is the simple way we can have the differential form of conservation of mass. Now this equation, I said, this equation, when this equation comes into picture for compressible flow, and if there is a incompressible flow, this term will be 0, means only this term will be comes into picture in the conservation of mass. Now second term is conservation of momentum in the differential form. The momentum describes the balancing between the force acting on the fluid element. So this describes the motion of the fluid particles by balancing the force acting on each and every particles, which is rho in the bracket dou v by dou t plus dot product of v nebula into v is equals to minus del p plus mu del square v plus f. So del p is the pressure gradient, mu v, nebula square v is a viscous force from the fluid friction, and F is external force such as gravity. Okay, so take the example water flowing around a cylinder. So near stroke equations predict how the velocity and pressure will develop around the object. So considering the forces like viscosity and pressure gradient. So this is all about the differential form of conservation of momentum. You can see the differences. Previously, we have this equation, momentum conservation equation. Now, this is differential form where we are involving the dot product in the particular part. Okay. Now, if we say steady flow, if we consider the steady flow equation, then what is steady flow? There is no change in the property throughout the flow. Means this term in the particular equation, if we say steady equation, this term will be 0, because we are saying the steady state means there is no change in the velocity with reference to the time. So dou v by dou t, this term in the case of steady state condition will be 0, and only this term. So rho dot product v del into v should be comes into picture, and the right side, as there is no force. If we are neglecting the external force, then this will be neglected in the particular equation, and final equation will be this one. Now come to the conservation form of energy, differential form of energy. So energy conservation describes how the thermal energy changes due to conduction, convection, and sources of heat. Now come to the final equation. Finally, we have energy conservation equation, which ensures that thermal energy change within the systems are due to conduction, convection, and any other source of heat. So rho E by rho T plus del rho EV will be equal to the minus del dot Q plus pi plus Q. So energy distribution due to the fluid viscosity, which we say it is pi. Q is external heat source, minus del dot Q is a heat gain or loss due to heat conduction. So this equation is used to generally used in the heat exchangers to predict the temperature distribution in the fluid flowing through pipes. It ensures that heat transfer through conduction, convection, and external heating is balanced. Okay, so there is a conservation of equation. There is a balancing of equation we are talking in the case of conservation of energy. Boundary conditions. There are two types of boundary condition. Dirichlet conditions, specified value, like temperature, pressure point at boundaries. Okay, means what I said. If suppose there is a fluid through the pipe. Okay, so I can give the temperature and the border will be 300 Kelvin, like that we can give. Okay, so it specifies a fixed gradient, which is partial T minus partial N, and mixed condition, which is combination of both Dirichlet and Newman condition. So initial condition, which defines state of the system at initial condition at delta type T, such as or such as initial velocity. Initial condition means this defines the state of the system at initial delta time T is equals to 0. So such initial, such conditions, we say the initial condition, like initial velocity, initial temperature at the entry of the fluid into the system. Okay, so these concepts too simple. Now let's take the example of water flow through a straight pipe. So equation for mass, momentum, energy will help us to understand how velocity and temperature varies within the, as per the law, as per the limits to equations, we can predict that if the fluid is flowing through the pipe, velocity at the border will be 0, neglected almost, it will be 0 at the border, and it will be maximum at the center. And in the case of heat, if we are providing the outer surface with the temperature, then the temperature profile means at the border, at the boundary, the temperature of the the fluid particle will be high, and it will be very less, temperature of the fluid particle will be less at the center. So differential formulation of conservation laws provides the detailed mathematical framework to describe the fluid flow and heat transfer. So which these equations are the base for the CFD simulation, and these equations only solved behind the softwares. Okay, so with this particular part, we can conclude our today's lecture. So hope you understand the topic. So what exactly differential formulation? These equations are derived from the conservation laws and represent fluid flow and heat transfer at every point in the domain. And application, it is used in the simulation of duct flow, external aerodynamics, and heat exchanger also. So these equations generally nonlinear, higher order, coupled, requiring numerical methods for solving those equations. And because of that, we need the numerical method, FDM, FVM, FEM. Okay. So that will be covering in the next coming days. So thank you for this. Now come to the subsidiaries law in the fluid mechanics. Yes. Subsidiary laws in the fluid mechanics and their role in the completing the main conservation law in computational fluid dynamics. These laws are essential for fully describing the fluid behavior and making the governing equations solvable. So what are subsidiaries law? The subsidiaries laws provides additional relationship that describes the material and thermodynamics properties of the fluid. Two key subsidiaries law generally we know is equation of state. This law relates pressure, density, and temperature. That is PV equals to MRT or P equals to rho RT, where rho is density. In the liquid or real gases, more complex equations of state like Van der Waals equation may apply. Okay, because whatever the state of equation of state we have, PV equals to MRT or P equals to rho RT, it is for ideal case. Now, constitutive relationship. So this describes how fluid responds to the forces such as shear or temperature gradient. Okay. For Newtonian fluid, the stress-strain relationship is linear. As you know, tau is equals to mu dou u by dou y. In the Newtonian fluid, shear stress is proportional to the rate of strain, which we express as tau is equals to mu dou u by dou y, where mu is the dynamic viscosity. For non-Newtonian fluid, relation is more complex and can be depend on the factor like shear rate, time, and temperature. Okay. Heat transfer within the fluid is also modeled using Fourier's law of heat conductions. As you know, Q equals to minus K rho T by dou X. Here Q is a heat flux and K is a thermal conductivity. So how these subsidiary laws complement the main conservation laws? Conservation laws introduce unknown like pressure, density, and space component. Subsidiaries laws such as equation of state, substitutive relations provide the extra equation needs to solve for those unknowns. Okay. Last time we have seen we have total 6 unknown, but as we know for 6 unknowns we should have 6 equations. 5 equations we have mass, momentum, and energy equation, mass conservation 1 equation, momentum equation 3 equations, XYZ direction, and energy equation 1. So total 5 equations we have, but for 6 unknown we should have 6 equations. So 6th equation will be provided by this subsidiaries law. Okay, so these subsidiaries laws provide the extra equations which needed to solve for the unknown. So material specific behavior, while conservation laws are universal, subsidiaries laws captures the unique property of each fluid such as viscosity and compressibility. For example, momentum conservation equation model force balance, while constitutive relations describes the stress-strain behavior. Okay, so thermodynamic coupling. So in compressible flow, the equation of state connects fluid dynamics to thermodynamics property by linking pressure, density, and temperature. So adapting to different flow regimes, subsidiaries law tailor the governing equations to specific scenarios such as laminar or turbulent flow by providing necessary flow specific parameter like turbulent viscosity. If we take the real time example, okay, for the compressible flow around the aircraft. The next two equations are derived from the conservation laws but are not enough on their own. So ideal gas equation of state like pressure, density and temperature will help us to give the extra equations. So constitutive relationship provides the viscosity and heat transfer behavior essential for modeling, modular and thermal effect. Without this subsidiary law, equation would lack the specificity need or to the model flow accurately. So subsidiary laws such as equation of states, constitutive relationships are indispensable in fluid mechanics. Okay, so thank you for this lecture. We will see the remaining topic in the next.